into the lab folder. Okay, and in the lab folder, I believe I'm going to have an SPSS version of this same file. I'm going to turn this to me so you can hear me as well. Okay, you should be able to hear me a little bit better now. And you may notice, let's see, single sample, two sample t-test SAV file. That's an SPSS data file, that SAV file. So I'm going to say, let's open this. Let's see, let's save the link as, actually, I want to open that file. Let me see what happens if I click it. Okay, it's going to, I just clicked it. I could download it to my desktop, but I clicked it and it says it's going to go ahead and open it in an SPSS. Now, hopefully, that'll have exactly the same data. In a moment, I'm going to show you how to import data from an Excel file to an SPSS file. For the moment, let's take a look at our analysis on this same data. Okay, so now here's SPSS. Okay, the first column represents our value for our two groups. And the second column represents gender. Okay, and in this case, let's see if this is coded. I'm going to go from our data view to our variable view. And sure enough, if I look at gender here, and click into the values, 1 represents male and 2 represents female. So someone has already coded this. Okay, when we import it from Excel, it may not be coded. Okay, but the way the data is presented, the actual values, whatever this X1 is, might be blood pressure, it might be height, it might be some test score or something like that, pain level, whatever it happens to be. This is the actual value that we're actually finding the mean of. Okay, and the second variable is a categorical variable. That's the variable that represents gender. I'm going to actually go in here into view, and I'm going to tell it to show me the value labels. So I can actually see what the 1s and 2s represent. And you'll see it's the same numbers, 6, 7, 14, 8, 10, same numbers as we had in the Excel file that we just analyzed, correct? And if you guys at home, one of you guys want to take a closer look at it, if you want to take a closer look at it, just make sure that they're exactly the same as the values that we just analyzed. Okay, so now I want to go ahead and analyze this. Okay, I'm going to go in here and I'm going to say, whoops. Oh, no, I'm looking at the wrong screen. Okay, I'm going to go here. And since I want to analyze this data, I hear a problem? No? I want to analyze this data. So naturally, I'll go up to the tab Analyze. Analyze. And I'm going to compare. What I'm doing here is I'm comparing the means of two populations, or comparing two sample means. Okay, so I'm going to go down into compare means. And I have a number of choices here. Remember before we did a one sample t-test? Okay, if I click on that, a box is going to come up and it's going to say, put the test variable in there. Put in the variable that represents that one, the sample that you have. Put in your sample here, and I'll analyze the mean. I'll calculate the mean and the standard deviation and compare it to a test value. This only needs one sample in order to do this, because we're going to put in what our mean was going to be. Like, for instance, is our mean before that we were comparing it to happened to be 10. We put a 10 in there, right? So we only need one sample and a value to compare it to. Okay, that's not what we're doing here, is it? Over here, we're going to analyze, compare means, but in this case, we're comparing two different samples. Okay, each with two different groups, each one having been sampled. Okay, two independent random samples. So I'm going to go down here, skip one sample t-test, go to independent samples t-test. Later on, we're going to take a look at paired samples. I'm going to click on independent sample t-test. Well, now I have to tell SPSS 2 bits of information. One is, what's the variable I'm testing? Okay, that's a variable, that's a numerical variable and numerical values that I'm finding the means of. And how are those grouped? Are those male and female? Are they grouped by hair color or whatever it is? Is it placebo and drug? Okay, in this case, it's by gender. So I'm going to move gender into the grouping variable. Now, SPSS is not very smart with this. Actually, it is smart with this. Let's say that I was grouping it into a hair color. A t-test can only compare how many means? 2 means, but you can have more than 2 hair colors, right? So maybe I want to compare blondes and redheads, right? In this case, I would have maybe 1 represented blondes, 2 represented redheads, 3 represented brunettes, 4 represented whatever other colors, right? So it's waiting for me to tell it which ones I want to compare. Okay, so I'm going to tell it I want to compare group 1 females versus group 2 males. Now, it's good that I looked at this before and I saw it was 1s and 2s. Otherwise, I might have been tempted to put 0 and 1, right? So I know it has to be 1 and 2. It's smart that way in that it knows to ask me which 2 groups. Since it's a t-test, I can only compare 2 means. It's dumb in that there are only 2 values there anyway. You would think a $1,000 program would see there's only 2 values and just fill them in for you, but apparently that's not that quite smart. Okay, so I'm going to put them in there, gender 1 and 2. Okay, so now I'm going to go ahead and I'm going to run my test. As soon as I do this, the output window is going to pop up. So we know our data window is one window. Our output window is a separate window. That's going to pop up. It's going to do the analysis and pop up. I like to do this twice in class because if I do it twice in class, I can scroll up and down a little bit. You don't have to follow me and do it again. And I'm going to click OK. Okay, so here we go. Let's see what it got. For the means for males, it got 2.739. Looks familiar to me, right? For the standard deviation, it got, well, let's not worry about that. For the means for females, it got 7.56. Looks familiar to me also. Okay, so now it went ahead and did our t-test. Okay, so let's look what happened in terms of the results of our t-test. Let's scroll this over. The first problem, okay, I'm going to scroll this over, and let's see. I have a whole bunch of columns here. First of all, there's a block of 4 things here, a 2x2 block right here, which looks like it's separated from the rest of this table, which in fact it is on purpose. Okay, that's Levine's test for the equality of variances. Okay, SPSS doesn't make a judgment. Oh, this one's twice the other one. Oh, I think maybe this group might be different, might have the same variance. I can't think of a reason why they wouldn't. It doesn't make that kind of judgment. It makes a mathematical judgment. And this is where it makes that judgment. We're going to ignore that for a moment. I'm just going to go across here to the actual t-test. So what does SPSS do? SPSS, number 1, calculates a standard difference error, right? And it calculates the standard error for a 2-sample t-test the same way we just did it by pooling the standard deviations. And what did it find the standard error was? 1.119. Isn't that the number we just got for standard error when we went through those two calculations? Okay, and let's see. The mean difference between them, right? The mean difference was 2.44 divided by 1.19. So it did the same thing we did to get a t-score of 2.18. Same value we got. So what's the t-score that we got here? The t-score that we got here was 2.184 for 16 degrees of freedom. It calculated the degrees of freedom we did, same way we did, N1 plus N2, sample size 1, 9, sample size 9, 2, 9, 18, minus 2 is 16. Same way we did, it got same t-score we did, the same degrees of freedom we did. It did it in a split second where we had to like struggle with a lot of parentheses and stuff like that, which I got wrong 4 times, right? So there's a lot of reasons for using something like this, right? Not the least of which is speed and accuracy, right? Or not the least of which is speed, accuracy being even more important. So now knowing this t-score, this degrees of freedom, we know we can reject the null hypothesis because we went to our table and we know that all this has to be is greater than 2.12, right? Right. So we reject our null hypothesis, right? So now, does this come to the same conclusion? Well, let's see. It doesn't actually say to reject our null hypothesis. It gives us an actual p-value. It uses the term significance, statistical significance for p-value, the probability of being wrong if you reject the null hypothesis. So what is the significance? What's the probability of being wrong? 0.044, right? Is that less than 5%? So since our p-value, our probability of being wrong, is less than our acceptable alpha error, 5%, what are we doing here? We're going to reject the null hypothesis, right? So in this case, we reject the null hypothesis. As it happens now, we know what the p-value is also. So it gives us a bit more. When we were doing the test, we could just say we reject the null hypothesis. Our p-value is less than 0.05. In this case, we actually know what our p-value is. Okay, let's go back to the right side of this thing here now. This is called Levene's test for the equality of variances. SPSS, before it does this calculation, or I don't know, who knows what happens first in this thing, right? It's happening in a millisecond anyway, right? It calculates a statistic called Levene's the F score for equality of variances. We use F for a lot of things in statistics, so don't get stuck on this F being the same as other Fs that we might work with. So what is this score? It's 1.456. As it happens, there's a distribution for this, just like everything else we're working with, a probability that's associated with this. It happens to be what is that, 3 or 2? Is that 2? That's 0.245, right? 0.245. So now, what is that? I got these progressive lenses. Anybody here use progressive lenses? If you're at the wrong, it's like, like for looking near, you like the bottom is right, and for looking far, and if I'm looking at an angle, I can't see anything because it's going to the wrong side. If I'm looking this way, so it's like especially these are relatively new, so I'm just getting used. I got to look at it exactly the right way. So anyway, you don't care about that. We got off on a tangent here. Okay, so let's see. If we were statisticians and we were going to set up a hypothesis, what would our initial assumption be? Always. Our null or initial hypothesis is always going to be that there's no difference, that the variances are the same for these two. Standard deviation, the variance, the same for these two groups. The same thing here. Equal variances assumed. That's our null hypothesis. We're only going to reject our null hypothesis if our probability of being wrong, our p-value, is less than, what do you think we should have here? 0.05. Is our p-value less than 0.05? Our probability of being wrong if we reject the null hypothesis? No, it's bigger than 0.05. So we don't reject the null hypothesis. What does that mean? That means we stick with the top row, which is based on a pooled standard deviation, equal variances and a pooled standard deviation. Had this been less than 0.05, what would we do instead? We would not assume equal variances. We'd use the bottom row. And the bottom row in this particular case turns out to be not very different than the top row in this particular case, right? The only thing that's really different here is the degrees of freedom. Remember that really funky looking formula that you saw in the lecture that came up with a number of degrees of freedom that wasn't an integer? That's what it actually calculated. It went through the entire calculation twice, using the formulas for assuming equal variances and using the formulas for not assuming equal variances, and it gave you the result for both, right? There's the result for both, right? And the confidence intervals here, remember you talked a little bit about the confidence intervals? That the real way to use confidence intervals here would be look at the confidence interval for the difference between the two means, right? That SPSS also calculates that, the lower and the upper range for the confidence interval for the difference between mu1 minus mu2. And in this case, the lower limit is 0.07 and the upper limit is 4.8 or whatever, right? So what does that tell you? That tells you that 0 is outside, no difference, or 0, x mu1 minus mu2, 0 is outside of that confidence interval. Don't worry about that. You really don't use that all that much. But that is a demonstration of what you saw in the lecture in terms of the right way to use a confidence interval, not for the confidence interval for mu1 versus the confidence interval you would see if they're overlapping, but seeing if 0 is really outside of the confidence interval. No difference between the two means is outside of the confidence interval for the difference of the two means. It sounds like a lot of big semantic exercise, but it does make a difference. It is different than the idea of comparing the overlap of the two intervals. Okay, so anyway, but the important part is that we would have stuck with the top row here, gotten our t-score, gotten our degrees of freedom, gotten our significance or p-value is less than 0.05, we reject the null hypothesis. You got two ways to do this now. You could do this manually, or you could do in Excel, or you could do this using SPSS. You have a third way to do this. What's the third way to do this? Anybody here using R? Okay. No, anybody using R to do this? You can use R to do this as well. Okay. Okay. I'm not going to demonstrate that here, but I mean it is conceivable that you could use R as well. Okay. Now maybe I could come up with a YouTube video or something like that where they do use it. But if you are using R, you prefer to use R, you don't want to use SPSS. Now, when you take the test, all of the computers you're going to be working on are going to have Excel and are going to have SPSS on them. Okay. So you'll have at least access to them, and I believe they have R on them also, if that's your preference. But you can use any one of them that you want. Okay, and if you have time, which a lot of times, you know, to be honest with you, we don't have a good perspective on this because we've seen this. Levi and I have seen this more times than we care to mention. So to us, the test seems like it should be something you could do in 20 minutes. But having been in your shoes many years ago, I can understand why it takes more than 20 minutes. You know, it's not, you know, from our perspective, it seems like you could have time to check your work both ways. But if you can stay organized enough, if you practice a little bit with the software, so you're not spinning your wheels a lot, you'll have time to you have more time than you think you really have. A lot of time is wasted in interpreting it and wandering around the software and not knowing, which one of the tests you should use and so on and so forth. But if you get comfortable with the software, it really will help you out. Okay, so let's move on to the next possible situation that we might run. Okay, so in the meantime, I'm going to switch back to my laptop, I think. Okay, for the time being. Let me see how I have to do that. Okay, let me think about this. Make presenter. Okay. Okay, good. And we should have my window back up there, right? Is my window back up there now? Yes. Okay. Okay. Oh, I'm sorry, guys, if you couldn't hear all of that. I tried to speak loudly and turn this thing in the right direction, so I hope you got at least most of what I was saying there. Okay, so let's go back to our sheet. Okay. Okay, let's take a look at the next problem. Okay, so two sample hypothesis test unequal variances. How are we going to solve that? I don't know how much time we're at 7:25 already, so I may start off with this and take a look at it in terms of our little description there on our sheet or on our spreadsheet. Excuse me, our PowerPoint on how we might do each one of these things. Let me just see if I can't get to it there. And let me bring this up. Okay, let's take a look at our formulas here. This was for situations where standard deviations are assumed to be equal. Okay, so let's take a look at the next situation. Samples where standard deviations are not assumed to be equal. Okay, well, what situation might that be? Well, you might actually see that when we sample males and females, let's say these are males and females, when we sample males and females, that the variability is so great that we don't want to make the assumption that they're equal. Okay, and I would only consider that if from your perspective, is if you calculate standard deviations of sample 1, calculate standard deviation of sample 2, and one of them is more than twice what the other is. In other words, one might have a standard deviation of 3, the other might have a standard deviation of 8 or something like that. Okay, where it seems like they're clearly different. Well, what happens then? Okay, well, what happens then is that your t-score is going to be equal to x, the mean for sample 1 minus the mean for sample 2 on the numerator. No different than before, right? Okay, the denominator now is different. instead of calculating a pooled standard deviation, you're going to calculate kind of like a geometric mean of the two standard deviations. Okay, so it's going to be the square root, and the denominator is going to be the square root of the standard deviation of sample 1 squared over the sample size of 1, plus the standard deviation of sample 2 squared over the sample size of 2, right? Those added together, and then the square root of that whole sum being taken together, right? Parentheses around the whole thing, okay? Then you're going to divide the denominator into the numerator, and you're going to get a number for a t-score, okay? So now you have your t-score. What's the only other thing you have to get to be able to know if you've exceeded your critical value? You need to know, in order to get your critical value, you need to know your degrees of freedom. That gets a little crazy. This is your formula for degrees of freedom. That's why we had, remember before, if we had used a line that was for unequal variances, you got whatever it was, 3.9297 or something like that. We got a crazy number so that's a rather obnoxious formula that we'd have to resolve. It's not impossible. I mean, if you look at it, it's really a bunch of squares and it's basically it's a mathematical formula. You could resolve that if you really wanted to. Okay, very frequently, if we're on a test, we may not have 20 minutes to do this and go back over it and make sure we got it right. So as a shortcut, you can say to yourself, well, if the sample size of one group is 9 and the sample size of the other group is 12, take the smaller sample size and subtract 1 and use 1 or 2. Levi, 1 or 2?
What?
For unequal variances, the degrees of freedom, shortcut, take the smaller sample size and subtract 1 or 2. That's pretty conservative. It's subtracting anything from it from the smaller sample size is super conservative. So subtract 1 from the smaller sample size. Sample size 9 and 11, you take 9, subtract 1, your degrees of freedom would be 8. That would allow you to look up on the t-table what your critical value of t is, and if your value of t that you calculated, right? This is no different than the calculation we did before, except we're using S1 squared and S2 squared instead of the pooled standard deviation in each case. Okay, in that case, if this t-value is greater than your critical value, you know your p-value is less than 0.05, and you can reject your null hypothesis. I know I'm killing you guys, right? It's all formulas tonight. I can appreciate that. I should have brought like a vat of coffee or something like that. I can tell because it really is challenging to keep up with this when this is happening. Okay, good. Okay, so now things are not done yet, right? Now we have another issue. Okay, and that is the idea of proportions, right? Not only do we often have numerical values that we're dealing with, but we also very frequently have binomial values. We have situations where we want to compare, say, the rate of a condition in a population, one population versus the rate in another population, or a drug group and a control group. Okay, so now we're faced with dealing with proportions. Okay, so now we could have two situations here, just like before. We could have a situation where we are comparing a proportion, take a sample, we're comparing a proportion to a known value. Okay, I'm not sure that I have a very good example of that. Let's see if we have a good two proportions hypothesis test. See if I got one single portion. Okay, so remember the problem that we worked out where we knew that 53% of the people in the population were going to vote for Mayor de Blasio, right? And we wanted to know whether, and it was a sample size of, I don't know, 300 people or something like that. What was that, 1,000 people it was? Okay, sample size of 1,000. We worked out that example. You can probably go, that's the last lab. You could go back there and take a look at it. And how did we figure that out? Well, what we need, that was a situation that was very similar to a single sample t-test. Okay, except that with a proportion, we're always dealing with large samples, so we use Z, right? So here we are, we're going to use Z, and we have a value which we know is going to be a value that we want to compare it to. Because it's an election and we want to know whether he's going to win a majority of the vote, the value we're going to compare it to is what? 50%. If his percentage is greater than 50%, we know he's going to win the election, right? So if there's only two people running. So we took a sample of 1,000 people. It appears that he has 53% of the vote, right? But that's a sample. That's not the entire population. So there's some variability in that. We might take another 1,000, get 52%. Another 1,000, get 49%, right? So we want to compare that value from our sample to a fixed value of 50%. That's almost the same thing as having a population with a known percentage. That's analogous to our single sample t-test. We have a sample proportion that we have a proportion for, and we're going to compare it to a known value. So how are we going to do that? Well, we're going to take the difference between the two proportions. The proportion for de Blasio, 50%, 53%, minus the proportion for winning or losing the election, 50%, right? That's going to be our numerator, just like we had x bar 1 minus x bar 2. That's going to be our numerator. And our denominator is going to be our standard error. Now, what's our standard error in this case? Well, since the proportion that we got from our sample was 0.53, right? How are we going to calculate our standard error? Anybody remember what the formula for that was? It was the square root of p times 1 minus p over the sample size, and then we take the square root of that whole thing. That's going to be in our denominator. So we're going to divide 0.03 by that standard error, and it's going to give us a t-score. And what does that t-score have to exceed in order for us to reject the null hypothesis? Well, it's a very large sample. It's a proportion, so we're going to use the z-score. So as far as z-score is concerned, if we want to be 95% certain, it's going to have to exceed 1.96 as our critical value. So with proportions, we're almost always going to be using the z-score as a critical value. If we wanted to be 99% certain, what would be our critical value? 2.58, right? Right. Okay, so I'm not going to actually work that out. That's the way that's going to work. Now, that's not often the case, though. A lot of times, we're going to be comparing one sample from one population to a sample from a second population, right? So, see, that's analogous to our two independent samples for that we were working with when we were working with the means just now. Okay, so let's take a look at that. What formula are we going to use for that? Well, population with sample sizes of at least 30 and at least 15 in each outcome. Okay, two population proportions. Okay, well, in this case, okay, we're going to calculate a pooled proportion for both samples. And how are we going to calculate that? It's going to be equal to the proportion for group 1 times the sample size of group 1 plus the proportion for group 2 times the sample size of group 2 divided by the total sample size for both groups. Okay, basically an average proportion for those two groups. And then how are we going to use that? We're going to take the proportion for p cap is the proportion for that particular group. Our z-score is going to be equal to our use pool p calculated above for p cap in the denominator. Yeah, that should be say p cap there, not pooled p. Okay, so at any rate, so the difference, the proportion of group 1. So if we're de Blasio were against, if de Blasio were 53%, his opponent were 47%. This would be 50.53 minus 0.47 divided by, and this would be the pooled proportions here. Pool proportion times 1 minus the pool proportion times 1 over sample size group 1 plus 1 over sample size group 2, square root of that whole thing, take the z-score of that, and compare that to 1.96. Okay, maybe we can give that a try. Let's see if we can't do that. I want to make sure we get the pooled samples though before we escape. Now I'm going to have two sessions. We have a By the way, alert, alert, we got a test coming up on Monday, right? That means, but then it goes for you guys online. So you guys have to be in here as well, right? So we have a mandatory attendance. So you guys can't like hang out at home next week. And you'll be getting more information from Levi and I on what's some sampling, some sample stuff on what's going to be on the exam and so on and so forth, and how much of this material which we're covering is going to be on the exam. I want to make sure we get to the paired samples before we get out of here tonight. I'm going to do 2 sessions, probably Wednesday night and probably either Saturday or Sunday for an hour each, so that we can go over all of this stuff. I'll post the answers to homework 4, so you have them, and I'll post a couple of examples. I know homework 5 is not due till after this, so I'll post a couple of examples because it includes some other stuff that goes into next week. I'll post some examples that you can do that we can work out during that other session. In addition to these. Okay, so let's take a look at this the two proportions hypothesis test. Researchers wish to test the effectiveness of a new antiviral drug for Ebola in clinical trials. 92 out of 200 people taking drugs showed improvement, while 64 out of 200 taking the placebo showed improvement. Okay, so what's PCAP1? Oops. Okay, why is it doing that? There we go. PCAP1. Okay, PCAP, let's see, drug. I'm going to keep ID is equal to 92 out of 200, which is going to be, what's that, 40.44546? 0.46? Am I right? That's 0.46. And PCAP placebo is equal to 64 out of, is it going to be 0.32? Right? Just a proportion. Right? 64 out of 200 is just 0.32. So we want to compare these two and see if the difference is due to chance, right? If we can reject them. So what's our null hypothesis? Our null hypothesis, H null, is that PCAP D is equal to PCAP of the placebo, right? Okay, our alternative hypothesis is that they're different. In fact, well, I'm not going to get into the idea of let's just look at different. Okay, we'll keep it single-sided. Single-sided is always more rigorous test, so you won't get criticized for keeping it single-sided. Okay, so let's compare the two of these. Well, our z-score is going to be equal to p-cap of the drug minus p-cap of the placebo, which is 0.46 minus 0.32. That's the top part of our equation, right? And the bottom part is going to be our standard error, divided by our standard error. So now we got to calculate our standard error. What's our standard error going to be? Well, if it were a single proportion, it'd be pretty easy, p times 1 minus p and so on. Okay, but in this case, where we're dealing with two proportions, okay, it's going to get a little bit stickier. We have to calculate a pooled proportion. So our pooled proportion is going to be equal to, I think I got somebody that's needs to be silenced again. Well, I got my speaker turned on too. I hope that didn't mess things up. I don't hear anybody complaining, so it must have been okay. Okay, so pool proportion is going to be equal to P, that's 0.46 times 0.46 times our sample size, which is 200, plus 0.432 times that sample size, right, divided by our total sample size, which is 400. Okay, that looks like to me it's going to be the average of those two proportions. Everybody agree with that? Right? It's going to be, what's that going to turn out to? 78 is going to be 39, right? That's going to be equal to 0.39. Am I right? Does that look right? 0.39? right? It's going to wind up just being the arithmetic average. Okay, so our pooled proportion is 0.39. It wouldn't have been just the arithmetic average if the sample sizes were different. In this case, the sample sizes were the same. Okay, so now I'm going to substitute that into my formula, and that's going to be, I'm going to pull up Excel to make this go a little bit quicker. We're going to be, if you got to bail out, go ahead and bail out when we get to that point. But I do want to do the last example, which is going to be a pooled, paired samples. So this is going to be equal to 0.39 times times 0.61, right? Times 1 over 200 plus 1 over, it's 2 over 200 is 100 is 0.01. Okay, I'm hoping that this will work. Oops. Okay, why is, okay, I need an asterisk here. Okay, and I'm going to take the square root of that. Okay, that turns out to be 0.048. I don't like that number. Something's wrong there. Uh, 0.39 times 0.16 times 100 to 100th 0.01. 0.01. Oh no, there's something wrong with that. Maybe I need to take this out of these parentheses. Right? That's got to be a very small number. I don't like that. Oh, I left the decimal point out there. That's what the problem is. Okay, and square root is equal to about 5%. My standard error is about 0.05. Okay, so now if I go down to here and I say to myself, well, 0.39 came out to be our numerator came out to be, right, what was our numerator? Our numerator came out to be 0.46 minus 0.32, which is 0.14, divided by our denominator, which is 0.05. Okay, and that's going to be equal to, I'm gonna just estimate that and say it's going to be about 2.8. So our z-score is 2.8 for the difference between these two. Can I reject my null hypothesis? Yes, I can, because I exceeded my critical value 1.96. Okay, last problem we're going to take a look at. Okay, paired samples t-tests. Okay, in this case, we have a drug test where maybe it's a blood pressure drug, and they have people taking a placebo for a couple of months, seeing if it affects their blood pressure, and then putting in a regimen with the drug for a couple of months. Some of these individuals take the drug first, randomly assign the drug first, or the placebo first. Some of them get the placebo first, and the drug first. The advantage of this is that, for instance, you start out with somebody that's got a blood pressure at level 6, right? And you see how the drug affects them versus the placebo, rather than comparing them to a different individual that starts out with a blood pressure at level 13, whatever that represents. Okay, so it makes more sense, right? You can see more directly what the effect of it is, and you reduce some of the variability in sampling that you might have. Okay, so these each represent the same person, right? So one of the ways that you might look at this, and I think I have this in Excel already set up as well. Okay, so paired samples t-tests. Oops, excuse me, that's the SPSS version. Here's our paired sample t-test, right? Instead of looking at the means for group 1 and the means for group 2, I'm going to look at the individual differences in these two groups, in each individual. Okay, so for the first person, there was no difference in his whatever that number is related to that drug. His reaction to the placebo and the drug were exactly the same. So I'm going to do that for each person in this group. Okay, and when I get to all of this, I see, well, some people, you know, when they took the drug, improved. Some people didn't improve. Okay, some people went the other direction. the drug made whatever marker of this was increase rather than decrease. What's the average difference? If there's no difference between the placebo and the drug, what would we expect the average difference to be? Zero. We would expect there to be no, in other words, half the time we would expect the person, the drug to be lower than the placebo. Half the time we would expect it to be more than the placebo, just because of chance. If the drug had no different effect than the placebo did, we would expect the difference for each person to be somewhere around zero, but not zero. But we'd expect the average for all of the people to be equal to zero. So I'm going to take the average difference. So now instead of analyzing group one versus the average for group one versus the average for group two, I'm examining the average for the differences for each person. So I'm no longer going to look at these values. I'm only considering these values. So what's my null hypothesis here? Right? My null hypothesis is not mu1 is equal to mu2, is it? Our null hypothesis is the difference is equal to zero. And our alternative hypothesis is that the difference is not equal to zero. Oops. Okay, so now how do we figure out if the difference is equal to zero or not? Well, same way as we always did. Now the difference is 1.55. We have to determine what's the chances that that difference is going to be actually equal to, is going to be big enough to be more than 2 standard deviations apart. And the way I'm going to do that is that my difference between the two groups is, my average difference is 1.5, and I'm going to compare that. I'm going to divide that by my standard error. And what's my standard error going to be? How's it going to determine my standard error? It's going to be a standard error of all these differences. Okay, so let's see, standard deviation of these differences is going to be 2.69, and the standard error is going to be equal to 2.69 divided by the square root of the sample size. Right? How big is the sample in this case? Is it 9 again? Yes, it's 9 again. So that would be divided by square root of 9, or 3. That's going to come out to 0.899. So what is my t-score going to be? It's going to be equal to the difference, 1.5, divided by my standard error, which is 0.89. My t-score is 1.66. Without even, what's my degrees of freedom going to be? It's going to be 8, right? It's only one sample. It's going to be 8. 9 minus 1. Without even looking at the t-table, I know that I failed to reject my null hypothesis because I haven't even exceeded 1.96, let alone what the critical t-value would have to be. Okay, can I do this in SPSS? Yes. If you look in SPSS, when I pulled down that drop menu, one of the selection was paired samples, right? And in that case, you would tell it the two groups, the two columns that you would have, right? And the two variables that you would have before and after, and it would realize that they match up row by row. It's the same person. And it would do this same exact analysis and give you a t-test at the end. Okay, it's not going to give you 2 rows though, because it's only working, it's a single sample test. So it's only going to give you 1 row in the result because it's not going to analyze equal variance assume or unequal variances assume. There's only 1 variance for your differences. Yes, was there a question? That's a good question. I presume you can. Do off the top of my head remember exactly how to do it? I'll have to look it up. I'll tell you what. Online. Ask me again when we have one of the sessions online. I'll figure it out. Okay. You guys want to spend the rest of the night here, or you're yawning? You're asleep? It's time. Good night, guys. Right? We're done, right? 7:50. Yeah, it's just about 7. Yes, of course. I got the 1.66 by taking the standard deviation of the. See, these things here, as far as I'm concerned, they no longer exist. Right? They're gone. Right? All I'm looking at is whether the average of the differences is far enough from zero for me to reject the null hypothesis. So I'm comparing, here's my mean difference is 1.55, right? That's like my X bar difference. That's my average difference. Okay. I want to know what my variability of these values is now. And the standard deviation of these numbers, I calculated the standard deviation to be 2.69, right? They use standard deviation. So now what is my standard error? My standard error is the standard deviation divided by the square root of the sample size. In this case happens to be 3, 9, so the square root is 3, so 2.69 divided by 3 is 0.89. So that's my standard error. So how many standard errors apart is 1.55 from 0? It's only like 1.66 standard errors. So I took 1.55 divided, and what's the formula I'm using here? Yeah. The formula here I'm using here is, the difference minus 0. Whoops. Let me do it this way. Difference minus what I assume I'm comparing it to, which is 0, divided by the standard error, right? Is what my t-score is going to be equal to. Boy, look at that. It's a weird window. Did you see that go by there? So, right, that's it. That's how I did it. If you look at the formula, if you look at the formula sheet I gave you, it'll be on there as well. I just had to rush. I had to rush it a bit here so that we could get that last test in. Get this last test in. Yes.
Is it correct that if you do a two-sample paired test, you'll get the same result? You'll do the difference if you create a new variable with differences and you do a one
if you do paired samples, you're more likely, it'll be easier for you to reject the null hypothesis than if you analyze them as independent samples.
But if you, okay, I understand that. But if you